Today I'm going to be going over cyclic acetal formation with you, and cyclic acetals are protecting groups for aldehydes, ketones, and diols. This topic can be a little bit tricky because it's hard to visualize and the products are usually a bit funky looking, which is why I wanted to go over this particular mechanism with you. So for the starting material for this super simple problem, I'm using a ketone, one equivalent of a vicinal diol, and an acid catalyst. And the first step is going to be to protonate the carbonyl oxygen. And this is going to give it a positive charge. And then the second step is going to be for that vicinal diol to come in and attack the carbonyl carbon. And then these pi electrons are going to push up to avoid pentavalency. And now the conjugate base is going to come in and deprotonate this oxygen with the positive charge, the one that just attacked the carbonyl carbon, to neutralize it. So now that that's been deprotonated, an acid catalyst is going to come in over here and protonate specifically the original carbonyl oxygen. And this is really important because it's going to create a water group that is going to leave and create a carbocation over here. And basically, this would create a much more stable carbocation than if this group over here were to be protonated and were to leave, because this carbon over here is connected to a heteroatom, which means that it is resonance stabilized. So make sure you protonate the original carbonyl carbon, the one that protonate the original carbonyl oxygen, because that one is connected to the carbon that's connected to a heteroatom. This is very important. Otherwise, this is going to lead to a series of mess ups, which you want to avoid. So we're here now, and this water group is formed, and it's going to leave and neutralize that oxygen. And now we have the carbocation, which is going to be attacked by this oxygen. And that's going to form this little ring structure that we're seeing. And the last step is for the conjugate base to deprotonate this oxygen and neutralize it. And this here is the cyclic acetal. This mechanism is pretty simple, although it is pretty similar to other mechanisms that you see for aldehydes, ketones, carb acid derivatives, because they basically all have to do with protonations and deprotonations. So you want to make sure that you understand exactly why something is being protonated or deprotonated, because just simply memorizing individual mechanisms is probably not going to work from here on out. It's really important that you understand why you're doing each step so that it all stays in your head. So now we're going to look at an example of where cyclic acetals are actually used as protecting groups. So in this example, this ketone over here is going to be turned into a cyclic acetal, and that would look something like this. And this is done because the reducing agent over here, LAH, would have reacted with the ketone to form an alcohol. And that was not the desired product in this example, which is why the cyclic acetal was made. And then in the second step of the reducing reaction, the acid from this is going to react with that cyclic acetal to revert it back to the ketone that we see in the product over here, since the acetal formation is a reversible reaction. So I just wanted to show that example of where it's actually used as a protecting group. Finally, I just wanted to go through one of the help session problem set problems with you, just because this one's a bit hard to visualize and it's also an intramolecular reaction. So again, the first step is going to be to protonate the carbonyl oxygen. And then the next step is for the diol to attack the carbonyl carbon. And the diol's already in the molecule, so we'll just have the alcohol come in and attack the carbonyl carbon. And the pi electrons will push up. So this step can be a bit hard to visualize just because this is when the ring is being formed. So my tip for you is to count the carbons in between the carbonyl carbon that's being attacked and the carbon to which the alcohol that's doing the attacking is attached. So if we go ahead and count these carbons, this can be 1, 2, 3, 4, and 5. So we know that there needs to be 5 carbons in this ring that's being formed. So if we count the carbons in the ring structure in the next step, and we make this 1 because this oxygen, it is the one that was on the carbonyl carbon. So we make that 1 again, 2, 3, 4, and 5, and we see that the alcohol that did the attacking is on the 5th carbon. We know that we did the ring structure correctly. So my advice is just to count your carbons after each step just to make sure you didn't accidentally delete a carbon or add a carbon where it's not supposed to be. That's probably the easiest way to make sure you're handling these more complicated intramolecular problems correctly. So moving along, we now have a positive charge on the oxygen that just attacked the carbonyl carbon. So the conjugate base will come in and deprotonate it. And now it's time to form the water group. And just a side note, this is the hemiacetal. Just thought I would include that in here. So now we need to bring in some more acid, and that original carbonyl oxygen is the one that's going to be protonated in this step. And remember, that's because it'll form the most stable carbocation, because the carbon that it's attached to is the one that's attached to the heteroatom over here. So next, this water group is going to leave, creating that carbocation, and then the alcohol is going to come in and attack it. But now it has a positive charge, so the conjugate base is going to come in again and deprotonate it for this final step. And this is the product. It's a bit funky looking, it's a little bit scary, but you should be able to do it as long as you're very careful with your steps and you're making sure to count your carbons and making sure you're protonating and deprotonating the correct things. So as long as you're able to form those patterns in your head and differentiate this mechanism from the carb acid derivative mechanisms and all those things, you should be good to go. Thank you so much for watching this video.